Hi, this is Team 31's presentation for Project 2, where a smog-free tire was developed and implemented in the city of Hong Kong. A brief introduction to the problem. Hong Kong has been facing several air quality issues for a number of years. The four main sources of these air quality issues is high concentration of NO2 particles from older diesel commercial vehicles on the road, emissions from marine vehicles and local power plants, as well as air quality issues from regions near Hong Kong. It's proven through studies that smog and air quality issues can cause severe health and respiratory problems for people in the area. Team 31 has used a smog-free tower to help reduce air quality issues to meet the World Health Organization guidelines for clean air, and that's been followed through the Hong Kong Clean Air Plan. In this presentation, Team 31 has developed a program that would model how particles are being captured from the air and how it's being cleaned, as well as the capture efficiency, and as well as from the model scaling up to help eradicate the problem in the entirety of Hong Kong, which is shown through the model and scaling up process.
This is Owen Johnson. I'll be discussing our computational model and the data gained from it. This model uses Euler's method to find the motion of a particle in 3D space given a known acceleration at each instant in time. Models can quickly become too complex to be useful, so Team 31 chose to focus the model on the particle's vertical motion. After all, most of the required complexity lies in gravity, buoyancy, drag, and electric field effects. These primarily act in the vertical direction. While horizontal drag might have some small effect in the real world, the assumption was made that wind speed would be sufficiently strong such that the drag from the plates would be negligible. The horizontal direction was not completely set aside. Each particle is modeled as having constant horizontal velocity, corresponding to the wind speed. When the model was run, it was observed that the particle reaches a constant terminal velocity extremely quickly. In fact, the model indicates that a PM10 particle reaches a terminal velocity of about 3 millimeters per second within a single millisecond. So, with the model, particles move at nearly constant velocity from almost the first instant of entering the plates. In addition, we found that the model produces the same velocity regardless of at which point the particle enters the plates. Simply put, every particle in the tower is modeled to have the same force applied to it and has the same terminal velocity. With this information, a metric was developed for estimating efficiency. You can see near the middle of the poster two black bars on a coordinate system. These represent a cross-section of two plates out of a large vertical stack of plates. The yellow arrows represent sample particles coming into the plates. If the vertical forces are applied, the particle paths will deflect as shown. Now I'm going to shade the paths of the particles that have collided with the plate. These particles have been captured, and it can be seen that any particle that enters below a certain height threshold will be captured. Efficiency is the percentage of the particles coming into the tower that are captured. It is calculated by dividing the area particles can enter at and be captured by the area particles won't be captured in. Because the whole system consists of a single stack of these plates, the efficiency between a single pair of plates will match the efficiency of the whole system. If we specify 100% efficiency, the spacing between plates must be equivalent to the capture height threshold. In terms of the diagram, the top black bar will be at the top of the transparent shaded section. This way, all of the particles that enter will be captured. A plot is shown of the plate width required for 100% efficiency versus the number of plates required to make a 7-meter high tower. This plot reveals the huge number of plates that would be needed for 100% efficiency, so it was simply used as a guide when selecting device parameters. To keep the number of plates reasonable, Team 31 selected a width of 2 meters. This would still require 3,000 plates, and at 1 millimeter thickness each, this would mean a significant area of the tower would be blocked by plate thickness. It would likely also make the zero horizontal drag assumption inaccurate, since the plates would be so close together. For these reasons, Team 31 selected 1,000 plates with 6 millimeters plate separation. At these specifications, 22% of particles that enter are expected to be successfully captured. Finally, the model was used to validate the conclusion that 22% of particles are captured. At the bottom of the screen, you will see the results of the model if a particle starts 1 millimeter from the bottom of a plate. The model predicts that the particle is captured. Now, another result. This time, from a starting distance of 1.6 millimeters, the particle is not captured. From the 6 millimeter panel separation, the particle cutoff distance is between 1 and 1.6 millimeters, or between 17 and 27% of the separation, and this supports the 22% efficiency conclusion.
So the team's first major recommendation due to the model is to face the tower to capture as much of the wind as possible. In Hong Kong, the prevailing wind comes from the northeast, and so the team recommends that the tower should face northwest in the orientation seen in the picture below. This allows for the open side of the tower with the slits between the plates to capture as many particles as possible. Since our tower is passive and doesn't actually suck in air, but needs the air to blow in on its own, this will allow for maximum filtration. The second recommendation that the team found is to use 1 millimeter thick panels made of stainless steel. This material was found to be the cheapest material that still offered a sustainability over time that could withstand weather elements and other factors. Finally, the team recommend that the tower be 2 meters by 2 meters by 7 meters tall. The model showed that overall size did not improve efficiency. With this in mind, a square base was chosen because it allowed for some key assumptions like the lack of drag in the y direction. This size also offered a stable efficiency with less cost than other options that were explored.
Based on the recommendations and the model developed by the team, in addition to some research based on different smog-free towers that were implemented in various cities such as Delhi and India and Beijing, China, and based on the materials used stated in the recommendations, an installation cost of $100,000 per tower was estimated with an operating cost of $8,250 per tower per year. And the team estimated that for Hong Kong, around at least 500 towers would be needed to eradicate the air quality issues, hence an installation cost of $500,000 and an operating cost of $4,125,000 per year for every year that the smog-free towers, and this is a minimum estimate of the total investment the Hong Kong government needs to make for eradicating the air quality issues that is currently present with the PM particles as well as different emissions from cars.
The current situation in Hong Kong is as follows. There's a PM10 concentration of 35 micrograms per meters cubed and a PM2.5 concentration of 22 micrograms per meters cubed. The goal is to have a PM10 concentration of 20 micrograms per meters cubed and a PM2.5 concentration of 10 micrograms per meters cubed. Using the efficiency from the model and data from outside sources, Team 31 was able to identify that within a 20-meter radius of the 7-foot tower, 22% of the PM10 will be filtered out. Furthermore, assuming that the lowest 100 meters of air is the most necessary portion that needs to be filtered, around 111 billion cubic meters of air will need to be filtered. Moreover, assuming that there's no more particulate matter being put out, Team 31 calculated that a single tower would need to run for 168,000 days, or about 500 years, to achieve the goal. However, this time frame could be reduced by adding more towers. For example, Team 31 calculated that about 460 7-foot towers could achieve the PM10 goal in a year.
Finally, long-term sustainability. The team decided that the smog-free tower does not present a long-term solution for Hong Kong. It was found that the tower is effective in open fields and in crowded places. And in crowded places like Hong Kong, it would be hard to find room for all of the towers to make an impact. With that being said, some towers could make an impact, a small impact, and last a long time. The stainless steel panels and low operating costs make it a long-lasting tower that will have some impact on the smog, just not reach our goal. In conclusion, we do not find that the smog-free tower to be a strong solution to the problem we were presented with, although it would work to some degree. Larger towers could reduce this problem and make it a better solution, but will increase costs significantly. This was Team 31's proposed solutions. Thanks for watching the presentation.